Okay. Hello, everyone. So Sandy is not here today, so I'm with this laptop. I'm trying to record the class so that he'll be able to see it. And if it works, I'll put it up on YouTube. But I'll send it out to everyone in case you want to look back at anything. Not quite sure how the levels will be on everything. So hopefully this works, but it might be a mess. Let's see what happens. Unfortunately, that our smart room is being used by another class that where they often take advantage of that technology, so we can't borrow it at this time. So we all survived the first round of presentations, our first module. I was impressed with your presentations. I think I was a little more lenient, being, it's kind of your first presentation in this class. So I think if we, just continue to grow, that we'll do well. And did you enjoy watching each other present and seeing different, it's kind of the same thing, but 13 times, right? But I think we can definitely learn. Everyone has their own style, and you definitely don't have to emulate someone entirely, but you can always see little things that you might have liked that you can use next time in your own presentation. It'll be a hazard today. Okay, here we go. So, second unit, Hick-Hyman law. Now, the chapter did a really good job going over it. There was a longer section on Hick-Hyman law, so I won't reiterate all of that content. But we will get to it in a moment. If you have any questions about the review, I'm happy to address those. But first, just want to tackle, I just had some general feedback from the presentations. And did I animate that? Oh, that's weird. I moved a circle. I forgot to copy it. So one thing I saw a lot of people do is they showed kind of like a screen, and they had a blue circle and a yellow circle. At the last moment, I move this one rather copy and paste. So, is this gonna work? There we go. So you showed something kind of like that here. I think you're trying to say, hey, there was a blue light and a yellow light. Just the one issue with this is it makes it look like on the screen, the blue appeared on this side, the yellow appeared on this side, or maybe vice versa. But remember, in the experiment, it was always one light kind of right in the middle. So not a huge deal, and within the context of that experiment, it wasn't a big deal. But what we're going to see in the next, even mostly in the next module, is that the side that the light appears on is a big deal. So it just caught me as a little bizarre, but I can see why it happened. So a better way to kind of describe what was going on there would be to show something like this. Or if you're going to do this, don't put a box around it so that it looks like a screen. Because when you do this, it looks like, oh, that's what appeared on the screen. And that is actually, these were a bit bigger. But over here, we didn't have lights on the left or the right. The other thing, this is obviously a bit extreme, but this podium or lectern, whatever you want to call it, it's unfortunately a bit big. And if you're tall, it's not as much of a problem, but you can see sometimes some of the presentations, I was just like, oh, who's back there? And it can definitely feel safer, being back here, but try to come out in front. I know that's something I might not do all the time, but even if you look at this image versus this image, and you can see that second one here, you're really focusing on the individual more. Especially have like a picture of me or something, like the neck down, wearing a suit there. Yes,
sir. You didn't have the clicker on, so we had to press to the keyboard.
True. The clicker didn't work for you. I think it did work later. And my standpoint on technology is it may or may not work. Kind of when I come in here to present, it's the same thing. But I mean, you can always be here, right? Sure. Going through your slides. And I think it's okay to return and then come out. The other one is white text. Actually, here does the white text look better than the black text on that slide? Yeah, oh, that's funny. So I was gonna say, white text is challenging, but I guess as long as you have enough contrast behind it, then maybe it's okay. So here, you know, if, let's say, you know, if your fill started to be light in color, then obviously the white text is very bad. So yeah, if you're going to do any white text, oh, I don't want to pull it anywhere. Just make sure you've got good contrast between your foreground and your background. And I think on my monitor, the black text looked a little better, but on the slides here, I think the white one's easier to read. So sometimes there's also a difference between, you know, your computer and then the screen. So just make sure you got good contrast. Any other comments from the presentations? So I was going to go over a few things that weren't in the reading, just I thought are interesting or helpful about Hick-Hyman law. Are there any questions about Hick-Hyman law? So basically, we're looking at the relationship between the reaction time and how many stimulus response alternatives there are. And Merkel was the original researcher to kind of see this relationship. And his plot was in the chapter. So, you know, reaction time increases, but not linearly. It increases a lot at first, and then there's this kind of a plateau or an asymptote. And this is a picture of the original device, at least where you would make responses. And I think the textbook mentions it briefly, but this is just telegraph keys. So for Morse code, where you'd be pressing a single key, and he took 10 of those and gave them a bit of an arc just so that they fit the fingers a little more comfortably than say having them all, you know, straight. That'd be a little weird. So his device, it's in a museum, I think somewhere in Germany. So hopefully one day I'll get to see it for myself. I don't think you're allowed to touch it. So, so yeah, that's what the input looked like. This is Hick. So almost 100 years later, 75 years later, and this is him in the lab, a very famous lab. A lot of research came out of this group in England. I forget which university now. But you can see he's fiddling with his input device here, which I think was also a series of telegraph keys. And here you can also see the stimuli. So I think these are like little light bulbs. So this is before they had LEDs, like the, you know, tiny status light in your phone. That's what we use now for this sort of thing. These are, I think, just basically tiny light bulbs. And I think this is a cork board, so that depending on the block, you can say, okay, you know, this one's 3 choice, so, you know, put in 3 lights and move all the other ones out of the way. Or, oh, now we're doing 8 choice, so we're gonna, you know, put a few more lights in there. I think that's just kind of neat to see. Well, that's, you know, doing this nowadays with a computer is a lot easier, obviously, than all this wiring. And maybe better precision electronics are, those types of electronics are really fast, which is nice. Here is a picture of Professor Hyman later on in his career. So sometimes you might see it called Hick law, sometimes Hick-Hyman. And basically, Hick did publish first in 1952, and he was a professor at the time. And Hyman, who was a PhD student, published the next year with a follow-up and some improvements and kind of some fixes to Hick. So in science, we really like to credit the first person, but because they were so close to each other, especially back then, 1 year wasn't as big of a difference. And because Hyman did kind of fix some things in the real Hick law, we often call it the Hick-Hyman law. So this photo, I found this online, and this is Hick here with his pipe, and he's in the previous photo he also had his pipe, but I don't know if he smoked a lot. But these other individuals are famous in this group, a British group that were some of the originators of cognitive psychology. This is post-World War II, I think, when this was taken, maybe in the 50s. And this is maybe the most famous individual. That's Alan Turing, who, if you know some of your history, he cracked the Nazi Enigma code. which they estimated shortened the war in Europe by 2 years and saved millions of lives. So it was a a huge accomplishment. So yeah, Hick-Hyman, they were in good company, really at the forefront of this kind of new wave of cognitive psychology. So this was in the text, and I think this is from Hick's experiment. Oh no, reprinted from Hyman. So this must be some of Hyman's data. And one thing I wanted to note here is these are 4 different individuals, and they've given their initials here. I guess none of them are Hyman himself, but everyone did 3 different experiments, and they put all their data in here. So you've got your reaction time. This is the number of bits of information. So, well, I guess we can assume this would be 0. So 0 bits, that's simple reaction time. This is 1 bit, so that's 2 choice. That's 4 choice, and that's 8 choice. So you can see that there is a logarithmic relationship between reaction time and the number of stimulus response alternatives. Or you could say, alternatively, there's a linear relationship between reaction time and the number of bits of information. Pete.
So I have a question. I was reading this part, and the slope is determined by what? The individual. So you have to measure first and then determine the equation.
Yes. Yeah, and that's what I kind of wanted to bring up here was the equation. So what you'll see is that everyone actually has their own Hick-Hyman equation. So they're not identical, and that's okay. And the Hick-Hyman law doesn't say, hey, you do this task and everyone will have the same line. No, it basically says that you will see a line, and it should have a positive slope. It shouldn't be a horizontal line. We actually saw that in some of the exception cases. So it should be a line with a positive slope. But depending on the individual, so if we look at the y-intercept here, where this value hits the y-axis, so it looks like it's about 200, and we can actually see the exact value here. Often, that equation is written y equals mx plus b is maybe the most common way to write it. It actually depends a bit on where you learn math. So I don't know if maybe that is what was most common in the UK, and that's why it's still like that in the textbook when they're presenting Hick and Hyman's data. So usually the equation of a line, we think of y equals mx plus b. Here they're presenting it as y equals b plus mx. But regardless, that is the y-intercept, 212. So for GC, that is their reaction time for a simple reaction time task. You bring them in, how fast are they at simple reaction time? 202 milliseconds. Now you wouldn't expect that to be the same value for everyone, and it isn't. So FP over here, their simple reaction time is 180 milliseconds. They're a bit faster. This person's even faster, 160, 165. So it's okay that everyone has their own y-intercept or their own simple reaction time. Now everyone's also going to have their same slope. So the m value, or how it's written here, it's in the second part of the equation. So this slope, so if you measure the rise over the run for this line, it's 153. Let's look at someone else here. They have a larger slope. Let's see who's got, oh, this is quite a bit smaller, that slope. So if we look at that line, it's got a steeper slope than this line. See, it's shallower. And what the slope tells you is how much your reaction time is going to increase every time you double the number of stimulus response alternatives. So here, as you go from 1 choice to 2 choice, so we've doubled the stimulus response alternatives, reaction time goes up by, 127. So it goes up by 127. Now, if we go from 2 choice to 4 choice, so we're doubling the stimulus response alternatives, reaction time is going to go up again by 127. 4 choice to 8 choice, doubled. Reaction time is going to go up the same value, 127 milliseconds. So if you think about, who's best at this task, well, it's good to have a fast, simple reaction time. So you want a low y-intercept or a value of b, and the shallower your slope, the better. Because as the task gets harder, if we compare 2 people, with the same y-intercept. So let's say each of these people has a y-intercept of 200, and one goes like this, and the other one starts at the same spot but goes like that. Well, this individual is better at the task. Because they're equivalent at simple reaction time, but as it gets harder and harder, so 2 choice, 4 choice, 8 choice, this person's reaction time increases much more on each trial than this individual. So if this were a sport, you would want this person on your team. So we look at these for, I guess this person's pretty good here. So they're not quite the fastest simple reaction time. This person's a little bit faster simple reaction time, but they've got the shallowest slope, much more shallow than this person. So although they don't win at simple reaction time, they are better at 2 choice, 4 choice, and 8 choice. So again, Hick-Hyman, they don't say everyone will show the same line. They just say that everyone will have their own line. And it should have a positive slope. No, it should be flat. That would be an exception. Definitely shouldn't be negative. I don't think we see that in any task, at least that I know of. So what we're going to be doing in the lab is finding the equation of your Hick-Hyman trade-off. The other time you would see these lines change is different people, and it would be more extreme. So if we test, well, we'll test all of y'all, and you'll probably have similar slopes and y-intercepts, not identical. But if we've got another group like children, or if we tested older adults, they would probably have very different slopes than you do. And that's okay. That's not breaking Hick-Hyman law or anything. The other thing that would change this, so even if I did this task, so let's say I used Merkel's original, keys, and then I did a different Hick-Hyman task. So maybe I now use the one that we're going to use in the lab with the keyboard and the monitor. Then your equation might be a little different because the task is different. Maybe one task is easier than the other. So you don't have an equation that's set in stone, but this will depend on the individual and on the task. So any questions about the equation? Now here, I don't actually like the way, there's 2 things I don't like about, well, first I expect the equation of line to be written like that. They're not using that exactly, and that's okay. But the other thing is, with the Hick-Hyman equation, you should solve all 4 variables, or you should put something in for each of those variables. So let's use participant LS here. So they discovered that this was, based on their data, 160, 190, what does that say? 190? 199x. So they've gone half the way, but they also should change x and y, not to a number. If we put in numbers for x and y, we'd be solving a point. We don't want a point, we want a whole line. But x and y, we should put in the values of our axes. So y, we should put in reaction time. RT is fine as an abbreviation, or you can spell it out as well if you like. Time. And then for x, the common thing to put in there is not stimulus information or bits, but how that's represented mathematically, which is log to the base 2 of n. So when you generate your equations, you should have something in for all 4 variables. And I guess the most common way, if you're used to the equation line this way, then feel free to use that. But I'm guessing most of us probably are used to it in this arrangement. Does anyone not use that one? Is that different than what they're used to using? So are we okay with the equations? Lee.
So you mentioned a 2, a 4, and an 8.
Yeah.
So why does it say 1, 2, and 3?
Okay, so what they've done is they've converted, oh, let's erase this. The easier way to do this plot, or an intermediate step to Hick-Hyman law, would just be to plot reaction time by the number of stimulus response alternatives, which we often call N. So we say, you know, there's one stimulus response alternative, or sorry, zero, oh, no, yeah, zero stimulus response alternative. We're gonna start this one at 1. So simple reaction time, 2 choice, 3 choice, you know, 4 choice. We could test all of these, right? We could go up to 10 choice with, if we're using digits alone. And when we plot these, so this is kind of like Merkel's original study. What they found is that you get data that looks something like that. So reaction time increases as we increase the number of stimulus response alternatives, but there's a very big increase from 1 to 2 in reaction time versus from 9 to 10. So, you know, why is that? Why, you know, we add 1 choice, we go from 1 to 2, or 1 stimulus response alternative, 1 to 2, big change in reaction time. Well, here we do the same thing. It's also +1, but we only go, we get a, you know, a tiny, tiny increase in reaction time. And what they said when they looked at this, they said, well, hey, this shape, what we're seeing, looks like a logarithmic function. And specifically, it looks like log to the base 2. So what the convention is on the x-axis, instead of plotting the number of stimulus response alternatives, we're going to plot log to the base 2 of the number of stimulus response alternatives. Now, why do we do that? Well, if this truly is a logarithmic function, if we transform the x-axis, we should see a straight line. And that's what we're seeing here. So all these data, if we plotted n instead of log to the base 2 of n, you know, we get that sort of curve, you know, kind of coming to an asymptote with higher number of choices. But then when we transform the axis, as has been done here, and plot log to the base 2 the number of stimulus response alternatives, we then see these straight lines. And as a scientist, we like straight lines because, 1, we know mathematically how to write the equation of a straight line. You know, we just y equals mx plus b, and we got to solve those 4 variables or put in axes labels for them. And it suggests that there's a very simple relationship between reaction time and log base 2 the number of stimulus response alternatives. So they transform their x-axis to prove that there is in fact a logarithmic relationship. We know there's a logarithmic relationship because when we transform the x-axis, we then see something that looks like a straight line. And we will probably see pretty good straight lines in all of our data.
I still have a question, because in the book, there's no mention of any studies beyond 10 choice. So I was wondering is it possible like to maybe use the tools or whatever?
Sure, yeah.
Because they mentioned like eye experiments, right?
Yep, yep.
I was wondering if in those they had more than 10. And if the relationship is maintained after 10.
Yeah.
What happens after 10?
I don't know. I was talking to Derek today, and I was saying, I wonder if you could, how long it would take to train your feet to be able to make individual toe responses. Because there's definitely individuals who don't have arms and they become quite dexterous with their feet. So if we could train people like that, we could try, 20 choice using, all of our digits and all of our toes. Are toes digits, or are digits only put around your hands? I don't even know. We need Dr. Areola here. But yeah, so with eye movements, you could do more because you can have, a lot. But I don't know. You couldn't have people looking at them because then we violate the Hick-Hyman law, but you could have people looking in the opposite direction. But I'm not sure. And we just only have so many digits, right? Any other questions about this relationship? So if you need to check out the reading again, because it goes into, I think, some pretty good good depth on talking about the theory behind this. And it presents it in a nice historical view from Merkel, who basically just showed this and said, hey, that's interesting. And then Hick-Hyman, who came along and said, well, that looks logarithmic. And then, they did this step and it talks about why that's of interest. So this is something interesting that I don't think is in the textbook, but we're always trying to find ways to measure intelligence. And I guess maybe I shouldn't say we. Within society, that seems to come up a lot. I don't think scientists are always trying to go, yeah, I'm not trying to do that. But it's one of those questions that is out there. How can we measure intelligence? And there was a suggestion that, well, maybe we can look at the slope of your line, and that would have a relationship to your intelligence. So remember we went back here, and we said that this person, had a really, this person had a really small slope. So they're better at the task than that person. So is there a relationship between this and intelligence? And if that's the case, that would be very helpful, because measuring intelligence with intelligence tests are hard and culturally specific. You can't probably even give a Canadian and an American the same test because their historical knowledge would be different. So you have to either maybe not test those forms of knowledge or have different historical questions. Like maybe the Canadian has asked who was the first prime minister, the American has asked who was the first president. So it gets complicated. So there was this suggestion that maybe there's a relationship between intelligence and the slope of your Hick-Hyman line. And I'm just going to look up because I forget the citation here. So there was a very small study done that looked at this, and they found a very small relationship. So it was a study in 1964, and there was a negative correlation of minus 0.36 between the slope of the Hick-Hyman equation and people's scores on an IQ test, the one they use. I don't know if it's relevant anymore, but Raven's progressive matrices test, which is one measure of intelligence. I don't think that's the best test that we'd be using nowadays. So they're like, okay, there's a relationship there. And did I mention the relationship between intelligence and height before? Did I muse about that one day? I didn't? Okay. I'm teaching 2 classes right now, and I find it hard to remember which class I told what. So there's also a correlation, there's a relationship between height and intelligence. So you might think, okay, well, let's make everyone taller and then they can be smart. So we didn't talk about this? I don't want to bore you about the same story twice. So, and that's potentially possible. I mean, we can't really change the height of adults, but we could make sure children have the best nutrition to end up taller. But when you look at the relationship between height and intelligence, to make someone significantly smarter, which is typically 10 points on a standardized measure of intelligence, they would have to be something like a foot taller. And that's not something we can accomplish with nutrition alone. So it's not something that has any practical value. And also we don't, there's a correlation, but we don't know the cause and effect. So why is that? Is it because in class you can see above everyone else, you've taken more on the board and then you're smarter? So yes, there's a relationship between height and intelligence, but it's so tiny, it doesn't really matter. And the question with this relationship between your processing, your slope and Hick-Hyman law and intelligence, it was the same sort of question. Like, well, sure, you found a tiny relationship. That study, I think there were like fewer than 10 people. So again, it's like, well, that's also a problem. So, does this actually exist? And I don't know why it wasn't until like the 2000s, so I guess 2000 exactly, that another group decided to look at this relationship. And I really want to reach out to these people and ask them what their idea was, because it just seems like it's kind of like a joke in general, but it's an actual study in a real, journal, a good journal. So what they said is, they said, okay, well, we could test humans. Let's find smart humans and stupid humans, but that's controversial, right? You don't want to do that. So they said, okay, well, let's compare humans to pigeons. And I think we can, without too much controversy, assume that the humans are smarter than the pigeons. And we'll test them both on the Hick-Hyman task, and we'll see who has the shallower slope. So they even tested two types of pigeons. I don't know if those pigeons are supposed to be smarter than each other. I don't know. But we can see that the pigeons here, and here are the humans. And the pigeons, it didn't seem to matter whether they were kings or rollers. I think those are kings and those are rollers, but I forget. It's been a long time since I made this slide. And here are the people. And the thing we're most interested in is the slope. So this is kind of written in the standard form where y equals mx plus b. Again, I wish that was reaction time, that was log to the base 2 of n. But what you can see is just based on the theory alone, that slope is what determines who's more intelligent. These results, tell us that the pigeons are more intelligent than humans. So it's either pigeons are more intelligent than humans, or there really isn't a useful relationship between your slope and your intelligence. But they went a step further. They said, well, wait a second. Maybe we didn't do this fairly. Because how did they test the humans? Well, they gave them the lights and they, made key presses. How did they test pigeons? Well, they gave them lights and then the pigeons would peck. So, okay, well, maybe that's why. So let's redo this experiment and let's have humans peck. So they actually did this. I don't know if the humans got to wear a little like cone or something on their nose, but they then pecked to the touch screen to be just like the pigeons. And actually human performance in this case was even worse, as you might predict. Their slope was even larger. So they're really, even when we try to make this as fair a comparison as possible, which seems kind of silly, there doesn't seem to be a useful relationship between your slope of your Hick-Hyman law and your intelligence. So when you all try this experiment, not the pigeon pecking one, but when you try this experiment in the lab, some of you will have different equations, and that's okay. It doesn't say anything deep about you. So is there a relationship? No. Or pigeons might be secretly plotting to take over. That is the alternative hypothesis that we cannot rule out just yet. So any questions about the Hick-Hyman law? Really need to email that group and let them know that I present this every year. I don't know. I mean, I'm not up with the pigeon research, so I don't know if that's a very well-known common study that everyone cites, but I always get a good chuckle when I get to present it. So now what I'd like to go over is more of the logistics of what you'll need to do once you get the data from this experiment. And the idea on this slide here is in our last experiment, MATLAB and that program did most of the data processing for you. So it ran the experiment, and MATLAB will always run the experiment, but in Donders, remember at the end, it gave you a number in each condition and said, oh, you've done simple reaction time, your value is this. And that was kind of, magical. It just spit out that value for you. And what we're going to do is through every unit, we're going to get kind of deeper and deeper into the measuring and the post-processing. MATLAB will kind of do less and less for us on that front. So in this experiment, we'll do some of the data processing. We're going to add to this a little each time. So I wanted to kind of take you through how that works today. So the way we're going to do Donders is we're not going to do everything from simple to 10 choice. We're going to do kind of the ones that have the easy powers of 2. So we'll do simple reaction time, and we're going to do this with the left hand and the right hand because we probably have slightly different reaction times between our left and right hands. Then we'll do 2 choice. Then we'll do 4 choice, and lastly we'll do 8 choice. So in 8 choice you'll be using your 8 digits, 8 fingers. Sorry, these are digits, these are fingers, these are thumbs, right? So let's look at this, for example. 4 choice, we'll focus on the data from this block, but each block, instead of it just spitting out a value, it's going to give you the result of every single trial. So for each block, you'll get an Excel spreadsheet, and you'll have to then, in that spreadsheet, do some processing to find out what your mean reaction time is in that block. So for choice, for example, there's 4 lights. One of the 4 will illuminate, and you would respond with these 4 fingers. So how many stimulus response alternatives are there? So we often abbreviate this as N. Lowercase or uppercase is fine. There are 4 stimulus response alternatives. How many bits of information are there? Well, we need to convert this log to the base 2 of 4 equals 2. And when you plot these, you should be plotting, the bits of information and not the number of stimulus response alternatives, because we want to see these nice straight lines. So here's our forward choice task, and this is what it will look like on the computer. You'll see the 4 kind of placeholders for the lights, and here you'd be using the D, F, J, and K keys. So the F and the J keys, like we used last time, those are the ones on the keyboard that have the little bumps you can feel. So you use your hands like this. So 2 choice would just be those. Simple would be one or the other, and then 4 choice you'd be using the other 2 keys on both sides. So those 4 lights placeholders appear. The fixation in the middle turns on, and that will last for half a second or 500 milliseconds. Then that disappears. So this is kind of like your warning signal saying, hey, you're about to get the go signal. Then you're going to have a random for period that'll last for 1 to 2 seconds. And that's randomized so that you can't predict exactly when the light will appear. And then after the random for period, one of the lights will illuminate. So in this case, it's the light where you should press the D key. So after a period of time, participants should press the D key. And the time between the go signal, the light appearing, and when you make the response, that is, of course, our reaction. So that's what the task will look like. Now, obviously, I gave a lot of the tiny details here, and in your presentation, you don't have time, of course, to give all that. So you can just focus on kind of the most important things. So how many trials do we have in these blocks? And again, this is, I don't expect you to replicate this in your presentation, but this you need to know to process the files. So in simple reaction time in those 2 blocks, it begins with 16 practice trials, and then there's 10 test trials. Now those go seamlessly from one to the next. And even in Donders' experiment, there were practice trials, but I don't tell participants about those. I guess we know about them now. But the idea is in your first few trials, your reaction time rapidly gets faster as you kind of warm up, get used to the task. We see that pretty much all the time. Even I've done a lot of reaction time tasks. If I tested myself right now, my reaction times would just start out slow and get faster. Maybe not as extreme as someone who's never done a reaction time task before, but I still sort of see that progression. So we throw in the practice trials to get to kind of more of a steady state of our reaction times, to get warmed up. So there are 60 practice trials, 10 trials, same, we use simple reaction time with the other hand. In 2 choice, same number of practice trials, but we doubled the test trials because we need to have 10 with this hand and 10 with the other hand. So you should have hopefully 20 good trials, and you'd be able to find the average reaction time for this finger and for that finger, for 10 trials for each of them. So obviously, once we get up to 8 choice, it takes a bit longer because we have 80 test trials, and there'll be 10 for each stimulus, and they'll all be randomized. Again, because it wouldn't work if it was, these 10 and then those 10 and then those 10. You would know what's going to happen. So it takes a little longer, I'd say, to do this one than Donders, but still not too long.
Is it also counterbalance?
Yes, the order of them. Yeah, I have that in the lab on it. So when you come in, we'll see this in the lab demo. But the first participant or whoever is going next, you'll know which participant you are, and then it gives you a random order to do the trials in. They're not counterbalanced because to do a counterbalance with 5 conditions, you actually have to have a 10-person counterbalance. So you should test 10 people or 20 people or 30 to be fully counterbalanced. And I mean, we're only going to test us, so there's only 13 of us. So the alternative is just to do a randomization, which is what I did. I just randomized, conditions 1, 2, 3, 4, 5 for each person. So when you come in, it'll show you the order to do. So the output from MATLAB at the end of the block will be a file. So in the code folder is the code that we run. Aside the code folder is a data folder where the data will be output. So they'll all be labeled block, output array, the letter P, and then this will be which participant number you are. So if it's 1, this will be a 1. If it's 13, it'll be 13. And then underscore T for type. And this number 1 to 5 refers to the type of block. So I think, well, yes, 1 is simple left, 2 is simple right, 3 is 2 choice, 4 is 4 choice, and 5 is 8 choice. So hopefully fairly logical. Within these files, they are comma separated values, which is like a simple Excel file. We'll open them in Excel. But this sort of format is great because you can open it in anything like MATLAB. And if anyone wants to use MATLAB, then I think that's actually great. And it would, once you know how to use MATLAB, it's much easier to use than Excel. We'll talk more about that in a moment. So what will you expect within the files? Well, there's going to be columns of data. So each row is a trial. And the columns, the first is the trial number. So that'll go 1, 2, 3, 4, and down. The second is the original trial number. We'll talk more about that in a moment. Then it'll have the 4-period duration. So remember, it's random, could be 1 to 2 seconds. Then the target number, so 1 to 8, and that goes from left to right. Then it says, is it a practice trial? This will be true or false. So 1 for true, 0 for false. And what you'll see is that the first 16 trials are always practice trials, where they'll be set to true. Then it has the participant's response. So this will tell you what they should press. This will tell you what they did press. And if it's the same, then they press the right key. And if it's different, they press the wrong key. And we should exclude that trial from our reaction times. And then lastly, their reaction time in milliseconds. I think that's it. Oh, there's one more. Yes, whether or not the trial was recycled. And I think there's only 2 reasons a trial would be recycled. So bad trials, if the computer detects you press the wrong key, or if your reaction time is less than 0. So you press the button before the code signal. I probably could have increased that to maybe a reaction time of 100 milliseconds, kind of be around the Olympic standard. But every once in a while I get participants in simple reaction time who might actually have reaction times more like 50 milliseconds. So I was like, okay, well, we'll only get rid of it if you press the button like way too early. So this will tell you if the trial was recycled, those are the 2 reasons why. And if they are bad trials, the program automatically adds them to the end of the block, and will eliminate the bad trial so that it doesn't bias our reaction time scores. So here are the target numbers, so left to right, 1 to 8. Okay, so let's look at importing the data. Now I have some data here from, I tried the experiment a few times myself, make sure it's working. So let's look at this block. So you can see here, this is participant 2, trial 4. These files will be .csv, it's not shown right here. And you can see there's another identical file. This one's .mat, so it's a MATLAB file. And if you do want to process your data with MATLAB, then I suggest you actually, save those files. They'll be easier to work with, slightly easier in MATLAB. So first thing that might throw you is if you just double click this and open up it in Excel, it doesn't open nicely. Older versions of Excel, actually, this did work. I don't know why it went from working to not working, but it doesn't work that way anymore. And what you need to do to open up a CSV file properly in Excel is, instead of opening it that way, just open up Excel and then go to data. We're going to go to the import area here. And we're going to say, hey, we want data from text or CSV. So that's what we have, CSV files. Let's see here. Let's find our data. Okay, so we want participant 2 in this case, and the 4th type, which is 4 choice. So we'll open this and it kicks off this import wizard. And now it will properly recognize that, hey, these data are in columns. Now, I don't know why it thinks there's a blank column at the start. There isn't. I tried playing around with this. It kind of always does that. So it seems like you just need to load it. And then you can just go ahead and delete that column. So here are our data. And if we go back, this is a description of our columns. So I'm going to add those in because, you know, it's kind of annoying this being numbers. It's hard to remember what things are. But at the same time, I'm just going to copy and paste these out of a document that I already went through and labeled. Let's see. So, oops, no, oh, well, let me do, oh, it's not gonna let me. How, oh, yeah, it's, oh, there we go, okay. I don't use Excel a lot, so you'll have to excuse my fumblings here. Okay, there we go. So we've got our trial numbers. This is 4 choice, so there should be 16 practice trials. All of them should have 16 practice trials. And then I think there was 40 trials after this. So this is probably going to go down to 56. And you can see it goes a little further, and that's probably because there are some bad trials that were recycled to the end. That we can actually pick out in a few ways. One, if we look at the original trial numbers here, that's going to go from 1 to 56. And then look, these are the trials that got added on to the end. So trial 31, the first time was bad, and it got repeated at the end. 32, 40, 47. So there are 4 bad trials that were recycled. These are the 4 periods for each trial. They're there. We're not really going to use them, but they're randomly determined and they fall between 1 and 2 seconds. Here's the target number. So on this first trial, it was target 3. So left hand, middle finger. And in this block, it should only be one of these. You shouldn't see a 1 or a 2 or a 7 or an 8 because it's 4 choice. You're not using those fingers in this block. It says, was it a practice trial? And what you can see is for the first 16, it always will be. So there's our first 16. They're all practice trials. These are not practice trials, so that means they're test trials. This is the key the participant pressed. So here they're supposed to press 3. Which one they press 3? So we know they pressed the right one. Let's see if we. But one way to find a bad one is just to look at whether the trial was recycled. So false was not recycled means it was a good trial. Let's find a recycled trial here. Okay, these 2 were recycled, bad trials. And on this one, they're supposed to press 3 and they pressed 4. And oh, this was the same one. Same mistake twice in a row. Most importantly, though, is our reaction time. So here it is to probably a ridiculous amount of precision. And we have that for each trial. So this is our basic file. We'll have 5 of these, 1 for each condition or block. And in simple reaction time, there'll be fewer trials. So it'll be a shorter file. And in 8 choice, that will be the longest file because it has 96 trials plus any if there are some recycled.
Are practice trials recycled?
No, that's a great question. So if you make a mistake on a practice trial, it doesn't recycle it. And that's basically the only reason that I tell the code which one is a practice trial, because then it doesn't recycle. It's like, well, that was practice anyway, so let's not bother. Yes.
And you're gonna email that to us again?
You can, after you do the experiment, you can pull the data right off there on the computer. So you don't have to wait for me to send it to you.
Do we email it to ourselves or something?
Either way, it's fine. I can also put it all up on Blackboard, but I'll probably wait until everyone's done and then upload it. So if you want it earlier, just grab it yourself. So we need to process this file, and that basically entails 4 steps. So you'll be doing this for each file, each of your own file. I'm not going to have you do everyone's files because that would take quite a bit of work. And really, that's where you start to see that Excel is not a great way to do this. Because sure, we can click through and do this 5 times, but if you had to do this 5 times 13 times, it starts to get annoying. And if we did an actual experiment that might have more like 40 participants, you start to go crazy. So what do we need to do to the file? We need to remove practice trials, not a big deal. We need to remove recycled trials, hopefully there's not too many. Then we need to remove trials with the left or right little and ring. Right little ring and left or right little ring and middle fingers. I don't know if I got my commas in the right places, but little ring. We're gonna get rid of trials with any of these fingers. Now, why is well, we'll come back to that and later. I'll show you why. You might already guess why. And then fourth, once we've processed the file, we can go ahead and calculate reaction time. So let's try doing that. First, we need to remove practice trials. And remember that every block, there's going to be 16 practice trials, so that's fairly easy to do. So I'm going to go to this file, and I'm going to get rid of the first 16 trials. So those are the practice trials. We're going to delete those. Done. Not too hard. Okay. Now, next up, so the slides here kind of, if you need to go back, it shows you, okay, well now you can see that the file should start on 17. So I won't necessarily show you all the slides because what we do is it's probably shown best by doing it in Excel. Now we need to remove recycled trials, and you could sort the data so that all the recycled trials are together, but there shouldn't be too many, so I don't mind just going and finding them. So I'm gonna look here. Okay, these two are recycled. I think there was only 4 in this block, so we're gonna get rid of those, the bad ones. This one, so you can see, I'm just looking to see when is recycled true for 1. Delete that. 1 more. And yeah, so now they're all 0, so that's great. So we are done, step 2. Step 3, so we want to basically keep trials just with these fingers. Now, why is that? Well, each finger reaction time would be slightly different. And to be as fair as possible, we're only going to use trials with our index fingers, which probably have the shortest reaction times because the index fingers, and I think the pinkies, are the only ones that have individual muscles that control them. And we do a lot of our, well, sorry, I'm leaving the thumbs that aren't I. Out of the fingers, these are the most dexterous. So they probably have the shortest reaction time. So we're only going to use those to be fair. So in simple reaction time and 2 choice, we don't have to get rid of anything because it's only these fingers involved. But in 4 choice and 8 choice, we need to get rid of these trials and these trials. So we're doing 4 choice right now. So this is target 1, 2, non-involved, 3, 4, 5, and 6. So we need to find all the 3 trials and 6 trials and get rid of them. And this is where it's probably easier to sort your data. So if we did this like recycle trials, we can say, oh, there's a 6, there's a 3. Okay, we'll get rid of those. So delete them and keep, delete, keep. Oh, I guess there's 3, so we gotta get rid of those. So that's gonna take a while. But what we can do is we can sort our data so that all ones with the same key press are together. Now, the way you don't want to do that is by using these things, because these will sort just the column just the column of data. So if we sort just this column, these will all change, but everything outside of it doesn't change. And now the values here don't line up with the other values. We want to sort it so that the whole row, wherever it moves, stays together. And the way you do that in Excel is you go into data here, click on sort. This is in the slides as well. And here it's because we imported the data, it already knows that those are the headers. And the nice thing about this is instead of having to pick A, B, C, we actually have the labels here to work with. So we want to sort the data by trial number. It doesn't really matter if it's smallest to largest or largest to smallest, but we'll say okay. And now it's sorted each row. It's kept all the data together, which is vital, but it's sorted it by target number. So see it does all the 3s, all the 4s, so they're all sorted. And we want to get rid of 3 and 6, right? So now it's easy to select all these. So I mean, if you want, you can go through, but this is probably faster and less likely to to result in a mistake. So there we go. We're left with just 4s and 5s.
So at the end of the day, we're always gonna have 25 left. Right?
Yes, provided everything works. That's a good check. So you can say, okay, do we have 10 trials here and do we have 10 trials here? The only exception would be is if there's a really bad trial that the computer doesn't catch and you make a note, oh, this trial was bad, and you want to manually remove that later. That would be the only reason that you have, fewer than 10 trials. Okay. So sorted data. Okay, we got rid of those. Now we're going to calculate the mean reaction time. And we're not going to calculate it separately for the left and right index finger. We'll just calculate a mean for all of those. And to do a mean reaction time in Excel, actually the function is average. And then you highlight the area you want. And because it's using this fancy table, if we look at the equation, it's identified, well, it's everything under this column with this name. So it's, usually you might expect it to say G2 colon G21, but it's being intelligent about how these tables work. So there we go. There's our reaction time. And I think I just rounded this to 1 decimal place. So we'll say it's 342.6. And that's it. You've got your first value from your first file. Now you're going to need to do that for the other 4 files. A few comments here. So in Excel, they call that an average. I don't like to use the word average in a scientific presentation, because the average, the technical definition is any measure of central tendency, and there are at least 3 measures of central tendency: the mean, the median, and the mode. So if someone just says I calculated the average, they might mean they calculated the mean. That's the most common usage, but it could rightfully mean that they calculated the median or the mode. And of course, those are very different things. So that's why I don't like using average, and it always bothers me that that's what Excel calls that function. So it's best to say whether you're using the mean, the median, or the mode, and not just generalize and say you used the average. Now, more recently, I discovered that there's actually different types of means, and some of you sitting out there might have realized that. So there's the arithmetic mean. That's the type of mean that we're used to. But there's also the geometric mean and the harmonic mean. Now, these ones, at least in kinesiology, are not used very much. So I think it's okay to say, I calculated the mean, and you don't have to say I calculated the arithmetic mean. There's a paper I'm working on right now where we actually use the arithmetic mean and the geometric mean, and in that case, I'm very specific about which one I'm using. But for your presentations, it's fine to say that you calculated the mean. Please don't say that you calculated the average. Okay, so you calculate the mean reaction time in each of the 5 reaction time tasks. I'm glad I put mean there and didn't get confused and put average. That would be funny. Now, in simple reaction time, you're going to get a mean reaction time for the left finger and for the right finger. In all the other blocks, we collapse those together. So you should do that for simple reaction time as well. So let's say it's 200 with this hand and 300 with this hand. Well, you should calculate the mean of those 2 hands, which would be 250. If it was 200, 300, 250, I think those are the numbers I gave. So you're going to end up with 4 means in the end. And for me, when I tried it, these are the means that I got. So in simple reaction time, this is the mean with my left hand. This is the mean with my right hand. So I calculate the mean of those 2 values, which is simply the midpoint. There's 2 choice. That's 4 choice. That's the one we did together. There's my 8 choice. And now what we want to do is plot those. And we're going to plot it by the log to the base 2 of the number of stimulus response alternatives. So we're not going to plot, 1, 2, 4, 8. We want to convert those from stimulus response alternatives to bits of information, which should be 0, 1, 2, and 3. So here's my plot in Excel. Now note that I made this pretty or prettier, at least when it comes out. So one thing when you do your plots, make sure they're legible I made these a lot bigger so they're easy to see. I put some labels up on there. I made sure that the axes were nice and tight to what I was looking at. So, the graph doesn't go, show from way down there to way up there. I also made sure there's not too many labels on here. That's kind of a pet peeve of mine when I see a graph and it'll say like 200, 210, 220, 230, 240, 250, 60, 70, 300. And then all of a sudden it's just crammed in there and it's hard to read. A great example of how to do this well, likely, is take a look at the speedometer in your car. And they usually, they don't say, it's not going to show 30 miles per hour, 31, 32, unless you have a digital display. But there's going to be breaks between those and little, hash marks for other numbers. So that has kind of a clean appearance to it. So that was my attempt at making a fairly clean looking display. So we've got the data. We need to find the equation of our data, and that starts by finding a line of best fit to our data. And in Excel, when you have your data selected, you can say add trend line, and it's automatically, okay, let's try it over here. It's automatically gonna fit a linear trend by default. Let's see. Oh, no, I need to go to this one where I have the okay. So here's my chart. Great. The colors changed in Excel to meet the to match the format. So select my data. I'm going to say add trend line, and it automatically throws on a linear one, which is what we want. And then the other thing that we probably want to add here is the equation of this line. So there we go. So there's the equation of my line, and you can actually go in and edit this still and change this to reaction time and log base to the end. There we go. And I think I even made this a little cleaner by rounding those numbers as well. Everything is possible in Excel. It's just a matter of digging to figure out how to do it. So there, I did not round those numbers anymore. Probably would have looked nicer if I rounded these, right? That's kind of silly to have that much. Maybe one decimal place. There, that's even better than it was before. So we've got our line of best fit, and you can manually go in and figure out, okay, what is the y-intercept? That's going to be the line of best fit when it hits simple reaction time. So we're no longer using these points to calculate the slope and the y-intercept. We're using the line of best fit. So if you calculate the slope of the line between these two dots, it's not the same as this whole line. So when we call the equation, it's based on the line of best fit and not the individual data points. So where does the line of best fit hit the y-axis? Right there, which is 240.9, which is not the same as that value. Now, what is the slope of the line of best fit? Well, it's 58.2, which is the slope of this line, but it's not the same as, the slope of, this line. That's a different slope. It's not the slope of this line. It's not the slope of that line. It's kind of a line. It's not even the slope of, any combination of these 2 points. It's the slope of the line of best fit. So there's my
so Hyman and Hick didn't have Excel. So how do they calculate the equation for their line?
by hand.
So they use the intercept and they use the difference between 2 points.
Oh, yeah. So, well, first of all, they have to get this line, which is kind of what we do in stats when we look at ANOVAs. You're actually basically fitting a line to data. So that's what we do with the correlation, and ANOVA is actually built on the same logic. So they would have used that formula to find this line.
There is a way to calculate an actual best line to fit them all.
Yep.
Okay.
Yeah, it's a mathematical equation where you're minimizing the distance away from the line at all your points. I'm sure I've done it by hand, but you don't have to. Excel does it very quickly. So what I demonstrated here was doing that all in Excel, and you're welcome to do it that way. I would encourage you to try using MATLAB. Now, you don't have to use MATLAB. Typically, it's harder initially to use MATLAB, but it pays off dividends when you have to do a bunch of data processing. For example, I've written a little script already that analyzes your data, and MATLAB doesn't care that much if there's 1 participant or 1,000 participants. It might take a minute with 1,000 compared to 1, but I just press play and it will analyze all the data. And you'll see kind of as you do this. I think it's also good to do it by hand so that you know what the data looks like. You don't want to become so automated that you're relying on a computer that spits out a magic number and you just go, oh, this must be right. So when I write things in MATLAB, I do things very carefully and I check along the way. So it's not a magic solution, but it's a lot easier. In this case, it's feasible to use Excel. As we proceed through the course, it will become more and more tedious to use Excel. It will always be possible, but in MATLAB, you can essentially write code so that it analyzes 1 trial or 1 block, and then you can then have it run through all of them without any really additional effort. Some more CPU cycles, but no effort on your behalf. So just think about this example. If I said, okay, in this experiment, you need to do that by hand for all the participants. So that's 5 conditions times 13 participants, 65. So that'd be 65 Excel files. That's not that much fun. Excel, you teach how to do it once and then it does it as many times as you want it to. I think it's important to kind of make a decision with yourself on how you want to proceed within this class, and either pick to go with Excel now or pick, I'm gonna struggle a bit early on, but I'm gonna use MATLAB. Because if you get to the last unit in this class and you then say, you know what, this is tedious to do in Excel, I want to use MATLAB. The challenge is we're going to be doing such complicated analysis that you're going to have so much catch up to do with using MATLAB. If you want to use MATLAB, it's easiest to start using it now when the analysis is fairly simple, right? We're talking about 4 steps. Remove practice trials, remove recycle trials, remove not index fingers, and then calculate the mean. That's not too hard, even in MATLAB. But if you get to the 5th assignment, you're like, oh, I'm going to jump on this MATLAB train. We're going to be too far ahead for that really to be feasible. And you can use either, and I'm both are fine, and I'm not going to judge you. Both are feasible, and your presentations, it probably won't even be obvious which you use. Well, I kind of can tell when a plot is MATLAB versus when it's Excel, but that doesn't really matter that much. So just think about kind of what you want to do, and if MATLAB is not going to be helpful for your future, then I'd say, well, maybe don't worry about learning it unless you want to, if you're curious. But that's just my little side spiel on MATLAB and Excel. Any questions about that? MATLAB is available to all students. You can go on eRater. It basically has you download it from MATLAB, and then it will give you a code to put in. Anyone can download MATLAB for free. It's just then whether you have a username or a license number to use it, and that's what eRater will give you. Okay, so for your presentations, we'll finish this, and then I guess on Wednesday we'll do the lab demo. But for your presentations, what I'd like to see is that you plot your data and calculate the Hick-Hyman law for your data based on the line of best fit. So if I were presenting, I would hopefully have a slide somewhat like this, maybe with those numbers around it, because that's not as pretty as I would like, where you show how this worked out, for you. The other thing I want you to show is how this worked out for the class. And that is where I will do some of the data, more of the data processing for you. So you have to do some work so that you generate this table, right? You're going to analyze those 5 files. What I will do is I will analyze everyone's data. And if you can imagine, each participant is going to have these 4 values. There'll be 13 of us. And then what I'll do is I'll calculate the average of all 13 participants. And that will yield 4 data points. And I'll send those to everyone. And then you'll use those to also calculate the Hick-Hyman equation for the entire class based on our average data. So you should present, your individual results, also the class results. We might not always do this because we're going to start adding variables in the next section. So we might have to, with 5 minutes, you don't have a lot of time to present a lot of data, but I hope we have enough time to present those two types of data. So I'll distribute the mean class data so that you have those. So yes, we'll start with the lab demo here, but that should be short. I'm guessing no more than 30 minutes. There are new sign up calendars on the lab door if you want to go in and pencil in at 4:30 on Wednesday if you want to do your data collection then. I will double check how long it takes to do the entire experiment. 15 minutes might still be enough time, but let me get back to you on Wednesday about that. Data collection will be due by the end of the day on Monday. And then by the end of the day on Monday or at least Tuesday morning, I'll be able to send you the class data. I can also upload individual data onto Blackboard, but if you want it before then, it just MATLAB outputs it into the data folder. You can find it there. And then we've got some time to work on presentations. I am around if you have questions, but we'll all meet on the Monday back here to do presentations. Any questions? All right, well, have a good day, and I'll be around for a little bit if you have anything you'd like to ask after class.
How did you bring those to us?
This was recording for Sandy.
Oh.
Oh, I think maybe you missed. I mentioned it before we started.